In this video, I am going to be showing you how to solve one of the infamous leaky bucket of sand problems, and you have three of them in the homework for section 2.5. All three of these problems, even with their minor differences, can be solved using the same procedures. So, a bucket which contains 15 kilograms of sand is to be lifted to the top of a 25-meter building by a rope with a density of 0.4 kilograms per meter. The bucket has a hole in it and leaks sand at a rate of 0.2 kilograms per meter. Find the work done lifting the bucket and rope to the top of the building. Now, this is a nice problem because it brings together a lot of the ideas from physics that we've been talking about in this section 2.5. The first one is work, which we've defined as a force exerted over a distance, and then force itself is mass times acceleration, and that usually means acceleration due to gravity. And acceleration due to gravity is the is gravitational pull, which is a constant. And in this problem, that constant will be 9.8 meters per second squared. And then finally, mass, we've talked about, is density times distance. Now, normally mass is density times volume, but if we're just talking about one dimension, a one-dimensional volume, essentially, we can think of as distance. All right, so to get started, we have to find work. And so work is force times distance, or looking at it from a calculus approach, we know that work is the integral from A to B of a force function exerted over a distance, which we're going to then represent as dx. So that parallels, as we've talked about in class, this formula right here. This would be more of an algebraic formula, and this is our calculus formula. And the differences with the calculus formula, we have variables that are changing. All right, so to use this integral, we need to have a force function. Well, we need to find the force function. Well, we know that force is mass times acceleration. And so since force is equal to mass times acceleration, well, as I just said, acceleration is going to be acceleration due to gravity. And so that acceleration is going to be represented by g equals 9.8 meters per second squared. So in these problems, we're going to be using this for acceleration whenever we need to. G is the acceleration due to gravity. So essentially, force is equal to 9.8 times the mass. Well, what that brings us down to then is we need to determine the mass. All right, and so we go to the third definition here, the third of these three. And so mass is density times distance. Well, we need to find the mass. We need to find mass of number one, the bucket. And number two, we need to find the mass of the rope. And when I say the bucket and the sand that is in the bucket. So we have two different masses that we need to determine. And that's what the crux of this problem comes down to. So first of all, let's find the mass of the bucket. All right, well, the mass of the bucket is given to us. The mass of the bucket is 15 kilograms. However, it's leaking. If it wasn't leaking, then the mass would be a constant, and this would just be reduced to a very simple problem. But because it is leaking, and it's leaking at the rate of 0.2 kilograms per meter, then what we have to do is we have to subtract 0.2 kilograms for every meter. And if we let x be equal to the number of meters, then when we have pulled it up 1 meter, it is leaking 0.2. When we've pulled it up 2 meters, it is leaking 2 times 0.2. So here is our expression, 15 minus 0.2x is our expression for the mass of the bucket. Well, now we need to find the mass of the rope. Well, the mass of the rope is not given to us, but it is given to us that its density. So remember that mass is equal to, the mass is going to be equal to density times the distance. Well, the density is given to us as 0.4. So that would be the density is 0.4 times the distance, which is 25 meters. And so that is equal to 10. However, so that's the density of the rope, 25 meters of rope, which has a density of 0.4 kilograms per meter. I'm not putting the units in here, but the units were given in the problem. This is 0.4 kilograms per meter, and this is 25 meters, so the total density is 10 kilograms. That's the density of the rope, the entire rope. However, the rope is being pulled up. So we're starting with 10 kilograms of the mass, but we have to subtract every time we pull up another meter of rope, we have less mass to pull up. And so because the mass is changing at the rate of 0.4 kilograms per meter, every meter that we pull up changes by 0.4. So this gives us the change in the density. So when we have pulled it up 1 meter, we're going to be 0.4 times 1, or 0.4 kilograms less than the 10 kilograms. When we pull it up 2 meters, 2 times 0.4, 0.8 kilograms would be subtracted from the 10 kilograms. So in other words, the mass is continually changing as we lift the bucket and the rope. So this now is our mass for the rope, and this is the mass that we have for the bucket. What we need to do now is we need to combine those masses. So the total mass total, is equal to the mass of the bucket plus the mass of the rope. And so the mass of the bucket was 15 minus 0.2x. And we have to add to that the mass of the rope, which was 10 minus 0.4x. And so let's simplify that expression. So 15 plus 10 is 25, and we have minus 0.2 and minus 0.4, so that's minus 0.6x. So that is our total mass. So all this work is just to figure out what that is. So now let's go back to our force function. Remember, we said that force, our force function, is going to be 9.8 times the mass. So our force function is 9.8 times 25 minus 0.6x. And simplifying that, we end up with 245 minus 5.88x. There now is my force function. So we're just using all of the definitions, kind of going backwards now. Starting with, we had to find work, but to do that we need to find force. To do that we needed to find mass. So now that we found the mass, we're finding the force function, and now we can put it together in the work function. So work is the integral, and so again we're lifting it from 25 feet, so from 0 feet to 25 feet. Our force function now is 245 minus 5.88x dx, and that is our integral that we are looking for. So on an exam, this is what I would be looking for, the simplified integral that you would use to solve this problem. And so actually doing the integration is going to be fairly straightforward. So the work is going to be 245x minus 5.88x squared, and that's divided by 2, evaluated from 0 to 25. So using the fundamental theorem of calculus and putting 245 times 25 minus 5.88 divided by 2 times 25. And then when we substitute 0 into all of these, we're just going to get one great big fat 0. And so doing this on a calculator on Desmos, we should end up with the work, if I did my arithmetic correctly, as 4287.5. That would be the amount of work being done. So all three of the problems in the homework that involve buckets of sand being lifted are all just variations on this same problem. All right, well, I hope you found this to be useful, and I will see you in class or at the review session.